think we can. So I'll do a couple of questions of molecules. जहाँ पे you've got primary, secondary, and tertiary alcohols. ठीक है? So here's a molecule, and this molecule has I mean, this is the skeletal formula of this molecule, and you have OH groups attached. There's an OH group over here. Okay, there's an OH group over here. There's an OH group attached on this carbon atom. So how many different types of alcohols you've got? The first thing is you have to figure out what are the different types of alcohols do you have in your molecule. So you've got this one. This one over here is it's bonded to 2 carbon chains. So this one is a secondary alcohol. This one over here, this one is bonded to, the OH carbon atom is bonded to 3 carbon chains on 3 sides. So that one is a tertiary alcohol. You've got this carbon atom, it's only bonded to 1 carbon chain. So that's your primary alcohol. So what's going to happen to each one of them? Primary alcohols, they are going to turn into, so the oxidation, if you react it with K2Cr2O7, so the primary alcohols over here will turn into carboxylic acids. So you're going to turn them into carboxylic acids. It will become double bond O and OH. So that is what happens to a primary alcohol. Tertiary alcohols have no oxidation. Tertiary alcohols are not going to get oxidized, and secondary alcohols will turn into ketones. So secondary alcohols are going to turn into ketones. This would become double bond O, that's it. So every type of alcohol will have a different reaction. Secondary alcohols are going to turn into ketone. The carbon, which was with the OH, it's going to turn into a ketone. You have primary alcohols that will turn into aldehydes, and then they will turn into carboxylic acids. Now, the other thing about this is that there's a reverse reaction as well, and that is reduction. So there's another reaction, which is exactly the opposite, and that is that the same molecules can undergo reduction. So we knew that primary alcohols turn into, we knew the forward reaction. We knew that primary alcohols, they are going to turn into, aldehydes. And aldehydes are further going to turn into carboxylic acids. We knew all of that. Okay, we knew the forward reaction. But the reverse is also possible. Forward is oxidation. Reduction is you're going to go back. Carboxylic acid will be turned into aldehydes, and aldehydes can be turned back into primary alcohol. So if you have a carboxylic acid, you've got a carbon atom that is a carboxylic acid, then that same carbon atom will be turned back into an aldehyde, and it will be turned back into an alcohol, the same carbon atom. So the reverse reaction is also possible, and all the changes that happen to the carbon over here, that's the reverse reaction. Now the reagents that are needed for this are, you need LiAlH4. That's your reducing agents. That's lithium hydroxyeliminate. So that's what's needed for the reverse reaction. And to convert aldehydes back to primary alcohols, what you can also use is NaBH4 along with LiLH4. Both are kind of the same thing, but turning carboxylic acid back into Aldehyde is slightly different, so that's a slightly stronger reducing agent. So it's a slightly stronger reducing agent. These are slightly milder oxide reducing agents. We're going to discuss the reducing agents in a while. Similarly, secondary alcohols used to get oxidized to, they used to get oxidized to ketones. So if you had a secondary alcohol is the one where the carbon with the OH, the alpha carbon, is bonded to two carbon chains. So that will turn into a ketone if you oxidize it. So that's the forward reaction, and but the same reaction could be turned, it could be reversed, and you would need a reducing agent which would be exactly the same. That would be NaPH4 or LiAlH4. So the same carbon that is forming a ketone is going to turn back into an alcohol. So that is reduction, and we're going to discuss the details of reduction first. I'm just going to give you a few examples. Like if I have a molecule and that molecule has ketones as well as aldehydes. So here's my molecule. And the molecule has a bunch of ketones. It's got an aldehyde. If it's right at the end, that's an aldehyde. And you've got a ketone here. And you've got another aldehyde over here. So what's going to happen when you try to reduce it? So if you try to reduce it, the only thing that's going to happen is keep everything exactly the same. The only thing that would happen is it's going to happen to the carbons over here. The only thing that's going to happen is it's going to happen to this carbon atom. They're going to turn back into alcohols. That's it. Remember, the end thing is like one of them is a carboxylic acid. Let's say one of them over here is a carboxylic acid. So remember, the rule is all of them turn back into alcohols. Whether it's a carboxylic acid, it's going to get reduced back to an alcohol. Whether it's a ketone, it's going to reduce back to a secondary alcohol. So you're going to do just that. Turn this back into an alcohol. So the whole carboxylic acid thing, all of them, they're going to turn back into alcohols. That's it. So this will have an OH. And this one over here will also turn back into an OH. All the ketones are going to turn back into alcohols as well. So this ketone over here, turn it back into an alcohol. So you rub it off and you just turn it back into an alcohol. That's it. So that is reduction of aldehydes and ketones and carboxylic acids. You must remember this chart, that what happens in this is that you've got a forward reaction, you've got a backward reaction. In the forward reaction, remember this. One second. So in the forward reaction, remember what's going to take place. So you've got a forward reaction. Forward reaction is primary alcohol turns into an aldehyde, turns into a carboxylic acid. The reagents that are required for oxidation are K2Cr27, KMnO4. If you want to convert aldehydes to carboxylic acid, the reagents are K2Cr27, KMnO4, but two others as well, toluenes and phenyl. And Similarly, if you have if you want the reaction to stop at aldehydes, what you do is instead of reflux, you use distillation instead of reflux. Secondary alcohols, they get oxidized to ketones. And the reverse is also true. In the reverse reaction, everything reverses. You've got aldehydes, they turn back into primary alcohols. You've got carboxylic acids, they turn back into aldehydes and primary alcohols and so on. So this is all about oxidation and reduction of aldehydes and ketones. Just 1 second. So I'm going to talk a bit about the mechanism of reduction, specifically for aldehydes. How are aldehydes and ketones reduced? Okay, just a little bit on the mechanism of the reduction process. So how are they reduced? And what is LiLH4? And what is NaBH4? I mean, both are kind of exactly the same things. So this one is a reducing agent. What that means is that reduction is a gain of hydrogen. So it produces hydrogen atoms. And the other compound is able to gain those H atoms. For example, over here, when you were doing reduction, you had oxygen and hydrogen. You had an oxygen over here, it ended up gaining hydrogen atoms. This oxygen over here ended up gaining hydrogen atom. These two ended up losing oxygen atoms. So reduction is, or a reducing agent is something that produces H atoms, because by definition, reduction, the definition of reduction is that it's a gain of hydrogen atoms. So this compound over here is made up of two things. One of them is a lithium ion, which is kind of irrelevant. The other one is the AlH4 minus 1 ion. So it's made up of these two ions. Now, if you look at aluminium, what happens is aluminium has 3 electrons in its outer shell. So it ends up bonding to 3 hydrogen atoms. But even when it does that, like if I draw the dot and cross diagram of Al with hydrogens, Al atom has 3 electrons. And you've got these tiny hydrogen atoms. They just have 1 electron each. So we need 3 of them. And they can ask you about the dot and cross diagram of lithium aluminum hydridoaluminate, LiLH4. So here's your aluminium atom, and if you focus on the aluminium atom, it's got aluminium is in group 3, so it's got 3 electrons. So it shares 1 over here, 1 over here, 1 over here, with 3 hydrogen atoms. Aluminium's outer shell is still not complete. So what it does is that it ends up forming a dative bond with an H minus 1 ion. So there's a 4th atom that comes in, but that 4th atom is a dative bond. A dative bond is something where the atom brings in all the electrons. Because aluminum doesn't have an electron, so aluminum needs 2 electrons to complete its outer shell. So H comes in and it ends up forming a dative bond, which is why AlH4 has a minus 1 charge, because H had brought in 2 electrons. So this one is a dative bond. So this is how this AlH4 minus 1 ion is a source of hydrogen atoms, because what happens is that this H atom tends to break away. So if it tends to break away, the H atom or H-1 ion is going to be produced back again. Remember, H has 1 electron, but in an H-1, it has 2 electrons. And the other thing will split. So this other thing is going to, it's going to split.
Sir,
Yes.
you know that tetraethyl alcohol, that doesn't reduce, does it?
Hey, which one? Tertiary alcohols?
Yeah.
I mean, tertiary alcohols don't get oxidized, so they don't need reduction. Like, they don't get oxidized to anything. You get my point?
Yeah, thank you.
So it's oxidation is forward, primary alcohols, aldehydes, carboxylic acid, reverse, you do it, that's reduction. Tertiary alcohols don't get oxidized, so they don't need reduction as well. Now the point is, why is this a reducing agent? It's a reducing agent because this AlH4-1 ion produces H-1 ions. What happens is the H-1 ions act as nucleophiles. So they act as nucleophiles and attack the carbon, which is positive. Like, for example, if you have a ketone, so why is the ketone going to get reduced? The reason it's going to get reduced is that the carbon is already very polar. It's positive, and the oxygen over here is partial negative. It's a polar bond. Oxygen is electronegative. So the H-1 comes in with its 2 electrons. And those 2 electrons are going to be very strongly attracted to this carbon, which is positively charged. And all the electrons in the double bond are going to be repelled upwards. So what will happen is that the nucleophile, which is H-1, which was very strongly attracted to the carbon, it's going to come and bond with it. The H-1 is going to come and bond with this carbon atom. And the electrons in the double bond, they're going to get repelled and they're going to accumulate at the top. Okay, so H-1, which is produced by the electrophile, by the reducing agent over here, which was busy producing H-1 ions. H-1 ions are going to attack the positive carbon atom. Remember, carboxylic acids, aldehydes, ketones, they all have C double bond O in them. So they all have this carbon, which is positive, and the H-1 comes in and gets attracted to this positive carbon atom, ends up bonding with it. And the double bonded electrons over here, because of the negative charge over here, the electrons in the double bond, they get repelled and they accumulate at the top. The next step is that the very next step is that eventually what would happen is that, there's water, there's aqueous ions, there would be H+1 ions floating around. Those H+1 ions are going to come in and they're going to join up with this. So this H+1 is going to come in because it's, H usually is +1. It's going to be attracted to this electrons and they're going to join up and form the alcohol back again. So this happens with every time there is reduction. So the alcohol will be formed back again. So that is how reduction is taking place. And that is how AlH4-1 is basically a source of, it's a source of H-1 ions. So every time you see this C double bond O, like if you look at this carbon, this is positive, the oxygen is slight negative. If you add AlH4-1 or NaBH4-1, the H-1 is going to get attracted. It's going to bring its lone pairs. It's going to get attracted to this carbon, which is positive. And the electrons in the double bond are going to get repelled. Same thing happens over here. You've got an H-1 lone pairs. The carbon is positive. The electrons are going to be attracted to this carbon. The electrons in the double bond are going to get repelled. And it would eventually turn into an alcohol. So the point is that every time a reduction happens, the H-1 ions are acting as nucleophiles. And this is an example of nucleophilic addition because they get added to it. Is this clear?
Yes, sir.
Do you remember they've asked you about this, although this mechanism is not in your course, but they have asked you about, in the questions, they have asked you about the dot and cross diagram of ALH4 minus 1. BH4 minus 1 is exactly the same because boron is also in group 3, so the outer shell electronic configuration would be exactly the same. So they've asked you about the dot and cross diagram. The role of the reducing agent is that it produces these H-1 ions, which go on to act as nucleophiles. It goes and attaches itself to the carbon, which is positive, and the double bond O turns into an alcohol during the process. Okay? So just remember this. And the next thing about alcohols we're going to do is, we've talked about reduction and oxidation. The next thing about alcohols that we're going to try and do is, it's this. I mean, the other ones are kind of simpler. Alcohols can be turned into, they can be turned into halogenoalkanes. Like if you have an alcohol and it's got these hydrogen atoms and OH groups, you can replace it with a Cl or with a Br or with an I. All you need is, there are multiple reagents that you could use. You could use concentrated HCl. You could use PCl3 plus heat. You could use SOCl2 plus heat. You could use PCl5. And similarly, if you want the OH over here to be replaced by, the OH over here to be replaced by not Cl but Br, what you can also do is, if you want another halogenoalkane to take its place, then it could be red phosphorus plus bromine plus heat, or you can call that PBr3. Or you could use HI. Or if you want, not HI, HBr. And the last one is, you can turn this into you can replace it with an iodine as well. So that would require red phosphorus plus I2 plus heat. Or number 2 is, you could use HI plus heat as well. So anyways, these are some reagents that would turn an alcohol back into a halogenoalkane.
Sir,
Yes.
you know the first thing that you wrote, the number 1 blue one, what does that say again?
The concentrated. This one is concentrated. So this one, okay, so I have a chart over here which kind of contains the whole, where's the organic division chart? So I've got a chart over here which kind of contains kind of all the reactions of that we have covered so far. What we just did was, we did this part, right? That I told you that, this is not very visible. So let me, So what we did right now was oxidation, alcohols, primary alcohols, turning into aldehydes, and aldehydes further getting oxidized to carboxylic acid. And carboxylic acid getting reduced, LiLH4. This is reduction. So we did all of that. Reduction, LiLH4 turns into aldehydes, and aldehydes further getting reduced to by NaBH4, LiLH4 back into primary alcohols. We did this part. What we are doing at the moment is the halogenoalkane thing, which I think is missing over here actually. So the halogenoalkane thing is, it's this one. Okay, it is missing. So let me. So this arrow over here, what's going to happen is that the alcohol will turn into a halogenoalkane. And the way it can turn into an halogenoalkane is you would have to react it with either, I mean, there were lots of reagents. So you can use PCl 5 or PCl3 plus heat. Okay, just copying this here. And if you want bromine, it's going to be red phosphorus plus bromine plus heat. There could be HBr. That could be used. You could use HCl. HI could be used. Anyways, plenty of reagents that could turn an alcohol back into a halogenoalkane. Now, further reactions of alcohols. Let's do further reactions of alcohols. There's another one, which is it given over here? Just a second. So there's another one, which is an alcohol can be turned back into an alkene. That's dehydration of alcohols. So it can turn back into an alkene. So let's do that one. So that's known as dehydration. I'll send you the chart which lists all the reactions. I'll send you a copy of the notes that we have made over here as well. So dehydration of alcohols. What happens in dehydration of alcohols? What happens is that if I have an alcohol and under certain conditions, and those conditions are, I mean, let me draw all the hydrogen atoms. So under certain conditions, which are, you can either use Al2O3 plus heat. So that is one of the conditions. Or you could use concentrated H2SO4. Those two, so it's or. You can use two conditions. What will happen is that the OH will be lost. It's going to go. And from the neighboring carbon atom, right next to a neighboring carbon atom, the H could be lost. So it could be an H that could be lost from the right side, or an H that could be lost on the left side. So this is what's going to happen. You can have multiple products. You'll have this one, you can have another one. So the OH will be lost, and from the neighboring carbon atom, an H would be lost. So, and a double bond is going to be formed in their place. So it will turn into an alkene. The same thing happens over here, but this time the OH is lost and the H is lost from the neighboring carbon atom that's on the left side. So an alkene is going to be formed. So you're going to get two different alkenes. One of them is butanene. This one is butanene. And this one over here is bute. Two-ene. So you're going to have two different alkenes as your product. Bute 1-ene and bute 2-ene. But always remember, whenever alkenes are formed, make sure that alkenes which have cis-trans isomers are treated as two different molecules. So this one, the second one, is going to have two different versions. It's going to have cis as well as trans. Like if you remember cis and trans, alkenes had cis and trans isomers. Like you had a double bond, and around the double bond, if the carbon atom was bonded to two different groups, and this carbon atom is also bonded to different groups, the molecule is going to have two different versions. Because around the double bond, the molecule is fan-shaped. So around the double bond, the shape of the molecule looks like this. And if the shape of the molecule looks like this, the double bonded carbon atom has two things attached to it. It's got an H and it's got a CH3. So there's going to be a CH3 and there's going to be an H that's attached. The other one, it's an H and there's a CH3 that's attached to it. So it's got an H and it's got a CH3 attached to it. The other one would be exactly the same, except that the positions of the H and CH3, they would be pointing, like the H is pointing, the H over here is pointing downwards. Over there, the H would be pointing upwards. This would be CH3 and H. So the only difference is,
So
yes.
Is this the one that has H up or down?
Is this the
one that has H pointing down or up?
in this case, both H's are pointing downwards, right? In this case, one of the H is pointing upwards, the other one is pointing downwards. This one was known as a trans isomer. And this one is known as a cis version. So remember, if we studied cis and trans earlier, whenever alkenes are formed, you have a double bond. And if the carbon atoms in the double bond are bonded to two different groups, like over here, it's bonded to two different groups, and this carbon atom is also bonded to two different groups, then they form cis and trans isomers. There's going to be two different three-dimensional versions of the molecule. There's going to be this one, where the carbon atoms would be pointing in like CH3 and H, and this would be CH3 and H, but the H atoms are pointing in the same direction. You have this one, H and CH3, except that the H is now pointing upwards. Hani, is this point clear?
Yes, sir.
So this is dehydration of alcohols. So whenever alcohols are dehydrated, they turn into alkenes. And they turn into alkenes, and remember this thing, that the OH is lost and the H is lost from any one of the carbon atoms. So we're going to do some questions on this. One thing that you have to remember is there are two ways of doing this reaction. There's a problem with concentrated H2SO4. Okay, there's a problem with the second reagent. So remember, with concentrated H2SO4, some of the alcohol, not all of it, some of the alcohol might be oxidized. As H2SO4, although it's a dehydrating agent, it helps in dehydration. But as H2SO4 is also a good oxidizing agent. So some of it might be oxidized as to remove acidic byproducts. Remember, alcohols, they turn into carboxylic acid, etc. So to remove acidic byproducts, the products are passed through an alkali or bubbled through an alkali. So the products are bubbled through an alkali. So this is just one simple point that, I mean, you're going to get alkenes, but what's going to happen is you'll get alkenes, but the only problem is that and alkenes will have cis and trans isomers. But the only problem is there's no problem with Al2O3, but with concentrated H2SO4, some of the alcohol might get oxidized, and you got to remove those other byproducts which are unwanted. So we're going to do some questions. Let's have an alcohol, and I'm trying to dehydrate it. So it's got an OH. So there's this OH here. Now this molecule is going to undergo dehydration. And you've got CH3 over here. So if you dehydrate this molecule, what's going to happen? We're trying to dehydrate this. Will there be multiple products or will there not be multiple products? So I've got, so let's say I've got these two molecules now. So I'm suspecting that there would be two different alkenes that would be possible if I dehydrate this. First thing, an OH will be lost from one of the carbon atoms, right? And an H would be lost from the neighboring carbon atom, but this one doesn't have a neighboring carbon atom. So that means you can't dehydrate this OH. Remember, if you look what you're doing over there, what would happen is that the OH was lost from one of the carbon atoms and the H is lost from the neighboring carbon atom. So you need a neighboring carbon atom with an H. Over here, the problem is the OH is going to be lost from one of the carbon atoms and the H would be lost from the neighboring carbon atom, but the neighboring carbon atom doesn't have any H. So kya hoga? Nothing would happen. Okay? I mean, this OH will not be able to, I mean, you won't be able to dehydrate this. What about this OH? OH would be lost from one of the carbon atoms and H would be lost from the neighboring carbon atom. And again, the same issue. The neighboring carbon atom has no H atoms. So that means there's not going to be any dehydration in this case. Is this clear? Anna, Hania, is this clear?
Yes, sir.
Yes, sir.
Achha, but what about this OH? This is going to get dehydrated. The carbon would be lost. I mean, OH would be lost from one of the carbon atoms and H can be lost from the neighboring carbon atom. Okay? So the two will go and they will turn into an alkene. Same thing happens over here. The OH is lost and the H is lost from the neighboring carbon atom. So you've got, so the double bond will form on the left side over here. So two different alkenes are possible. One of them is this, the other one is this one. These alcohols are not going to get dehydrated because the neighboring carbon atom doesn't have any H atoms. So you're going to get two different alkenes. Can you even spot which one of them will actually be forming cis and trans isomers?
First one.
Okay, the first one will be forming cis and trans isomers because you got a double bond and over here, two different groups are attached towards on this carbon atom. Same thing over here, you've got two different groups attached. So this double bond in 3 dimensions will exist in 2 forms. One would be cis and the other one would be trans. So this molecule, there would be actually 2 different molecules. One would be a cis version and the other one would be a trans version. This is not going to form cis and trans like this one. It's not going to form cis and trans because you got a double bond, but the carbon is bonded to the same groups. So 3-dimensional, even if you switch the groups around, the H is pointing downwards, this H is pointing upwards. It doesn't really matter because it's going to be the same thing. So you'll have 3 different products. 2 of these, 2 versions of this and 1 version of this. So is this clear? Dehydration. Everyone, is this
So
clear?
could you please
Yes, sir.
explain this cis and trans thing again?
What's this thing, right? That whenever you have a double
No,
bond,
like why the first one can't make cis and trans, because my mom was talking to me, so I couldn't hear.
the first, this one, right? Remember, what's the rule for cis and trans? You got a double bond, and the double bond, the carbon atom must be bonded to 2 different groups. So this carbon atom is bonded to 2 different groups. It's bonded to an H, and it's bonded to a CH3, right? This carbon atom, it's also bonded to 2 different groups. It's bonded to an H and a in this entire thing, right? So it's going to form cis and trans. Like you can think of it this way, that this one is bonded to an H and it's bonded to a carbon chain over here. This one is bonded to an H, it's bonded to a carbon chain over here. So the 3-dimensional shape of this molecule is going to be, the molecule is going to have 3-dimensional shapes. Around the double bond, it's fan shaped like this. So there's an R, there's an H pointing downwards, and R, there's an H pointing downwards. And there's going to be a different version of the molecule where the bonding would be exactly the same, except R and H. But over here, the R is pointing downwards and the H is pointing upwards. Is this clear? Hania, is this clear?
Yes, sir.
So let's continue with this. We just did this part. We're almost done with oxidation. We did dehydration of alcohols, which is this one, Al2O3 plus heat or concentrated H2SO4. So we did that. We did oxidation of alcohols and reduction of alcohols. We did alcohols turning into aldehydes, turning into carboxylic acid. These were the oxidation reagents. You want to go back, you use LiLH4, you use NaBH4 or LiLH4, you go back. So that is reduction. Okay. So we did 2 things, and we also did this thing. You can turn an alcohol into a halogenoalkane by reacting it with, if you want chlorine, you want bromine or HI. So here, let's continue tomorrow then. Okay, everyone.
Thank you, sir.
Love it.
Love it.
Mhm.